Hi, and welcome to the Port of Oakland. Ships from all over the world come here to deliver a wide variety of goods from overseas. They also come here to pick up goods to take back to Asia, Australia, Europe, Africa, and all points in between. But we're here today to do some carpool chemistry. Today we're going to take a look at some double displacement reactions. Let's say you have a reaction between magnesium nitrate and potassium hydroxide. On the surface, you may ask yourself, well, hey, what do these two compounds form when they react together? Well, knowing that it's a double displacement reaction, you can figure it out. I like to use, for example, the royal couple from across the pond in jolly old England. And we know that they are William, Prince William, and Kate. They're a married couple, and I'm going to abbreviate William with W, Kate with a K. And then there's his brother, Harry, who's married to Meghan. They're also a couple, and Harry will be abbreviated with an H, Meghan with an M. I'm going to assign these abbreviations to our two compounds in this equation. We're going to call magnesium William. We're going to call the second part of this compound, nitrate, Kate, or K. The second compound, we're going to call the first part Harry, and the second part, hydroxide, Meghan. I'm also going to put a parenthesis around this OH to indicate that, hey, this is the hydroxide ion. It's a polyatomic ion, shown right over here with a -1 charge. So you may ask, what do these two compounds form when they react? In a double displacement reaction, what happens is that the couples would change partners. Now we know in real life this would never happen, especially with the queen at the helm. But if it were to happen, let's take a look. William would end up with Meghan, and Harry would end up with Kate. So how do you say William? William is magnesium, and Meghan is OH. And we know once again from our oxidation number table that magnesium, when it forms ions and bonds with other elements, takes on our +2 charge here. So I'm going to put a +2 here. Hydroxide, like we just mentioned, takes on a -1 charge. And how many of these -1 hydroxides do we need in order to form a stable neutral compound with this +2 magnesium? We need 2 of them. That gives us a -2 charge from the hydroxide, +2 charge from magnesium. Overall, a neutral compound. Plus, and the other item that this forms, well, Harry and Kate. Harry is potassium, and Kate is our nitrate ion, NO3, and that's right over here, and that has a -1 charge. Now you may be tempted to carry this 2 over to the right hand side. That may or may not be the case. We need to check the charges to make sure. Let's take a look at potassium. Potassium is a +1 charge. Let's put a +1 here. We have +1 from the potassium, -1 from the nitrate. It does not look like we need a 2 after the NO3. It looks like it's stable and neutral as written here. But we'll take care of the imbalance right now when we balance this equation. So our next and final step is to write the balanced equation. And what I like to do is to put a blank before each term. And what this does is it forces me, when balancing my equation, to only change coefficients and not subscripts. Because as we know, if we change the subscripts of these compounds, it actually changes the formula and the chemical makeup of it, which is not what we're here to do when we're balancing the equations. We want to start off with the metals. Magnesium is a metal, so we have 1 magnesium on the left, 1 magnesium on the right. It looks like we're balanced. We don't need to change anything. Another metal here is potassium. 1 potassium on the left, 1 potassium on the right. We look like we're okay on potassium. Let's go with the polyatomic ions next. Nitrate is our first polyatomic ion. We have 2 nitrates on the left, and we see only 1 nitrate on the right. So we want to put a 2 in this blank, because this 2 applies to this entire bundle, meaning 2 potassiums and also 2 nitrate packages. So our nitrates are now balanced, but when we put this 2 here, it just changed the balance of our potassium. So what we need to do is go back over here, and in this blank in front of the potassium, put a 2. Now that works out well also, because if we take a look at our final piece over here, the hydroxide, because this 2 applies to this entire bundle here, we also have 2 hydroxides on the left, and we see 2 hydroxides on the right-hand side. Our equation is now balanced. And that's how you do a double displacement reaction. Thank you for watching. From the Port of Oakland, this is Carpool Chemistry.